Rainers as our guest speakers from Nanyang Technological University, NTU Singapore. And Prof. Rainer will speak about towards scalable quantum hardware, innovation, and in electronic control and quantum processors. So it's my pleasure to welcoming Prof. Rainer. How are you today, Prof. Rainer?
Perfect. Thank you. Thank you. Yes.
Okay, thank you for being with us today. And the first, please feel free to share your screen.
Okay, sure. Yeah, let me share the screen. Just give me a second.
Okay. Before we start, please allow me to briefly introduce our speaker. Okay. Prof. Rainer received his PhD from Leibniz University in Hanover in Germany in 2003, and his PhD journey included positions as Junior Research Fellow at the National Institute of the Standards and Technology in the United States. And following his doctorate, he was awarded the prestigious Alexander Van Humble Fellowships, allowing him to return to Nice in 2003 to continue his research about ultra-cold molecule and quantum degenerate gases. And in September 2005, he joined the Max Planck Institute for the Science of Light in Erlangen, Germany, as a postdoctoral research fellow. And Prof. Rainer joined in the Nanyang Technological University in Singapore in 2006. And he is currently served as associate professor in the School of Physical and Mathematical Science. He is also a principal investigator at the Center of Quantum Technologies, National University of Singapore, and his research mainly focus on quantum circuit and sensor. So it particularly focus on hybridizing atomic and also superconducting technology for quantum computing applications. So with that, Prof. Rainer, you have 1 hour for your presentations and 30 minutes for the questions and answer sessions. So please be informed to all the participants. So if you have any questions during the presentation, please post your question in the chat. And for Prof. Rainer, if there are any questions that appear in the Zoom chat during your presentations, please ignore them as I will read the questions after I finish your presentation. So Prof. Rainer, the floor is yours.
Okay, thanks. Thanks, Marcus, for the very, very kind introduction.
Okay, you're welcome.
And again, thank you for inviting me to give the presentation about, let's see, what we are doing here in Singapore and the research we are doing. Maybe I will, let's say, I will talk about, let's say, particular quantum computing and the quantum hardware which we are developing. Of course, this development is not done, let's say, by me alone. I'm just the group leader. I have, let's say, a large team of researchers who actually do the real science in the lab. One of them, for example, is Ranga Budoyo. He is also from Indonesia and has, let's say, a very strong background in superconducting quantum computing. He's actually one of the pillars in this research area here in Singapore. Okay, so maybe let me just progress and talk a little bit about quantum technologies in general, right? There's right now a lot of interest in this type of technology, and there are, let's say, 3 main areas of quantum technologies, or 3 main application areas of quantum technology. One is quantum computing and simulation, quantum communication, where you can actually send information encrypted over a long distance without being physically possible to actually eavesdrop on this communication. And there's, let's say, the last area is quantum sensing, where we actually develop also sensors which have sensitivities and accuracies much higher or much beyond what classical sensors can actually do. However, in this talk, we will just focus on quantum computing and simulation. As a side remark also, just a few years ago, 2022, there was in this area actually a Nobel Prize awarded through 3 scientists in exploring the quantum weirdness, right? It was Elena Spee, John Clauser, and Anton Zeilinger. And this was actually the award towards the secure communication, which I mentioned before, and quantum computation. So it's a very, let's say, interesting topic, and actually sits on the, let's say, work of giants. Okay, so maybe let's first go, let's say, one step back. Let's think about what is actually a classical computer, or what is, let's say, the difference between a quantum computer and a classical computer? Is it just sort of the same as a classical computer, just bigger? Or is it something else? To actually understand how it is actually different, we may want to think about how, let's say, basic classical computers working, or what are the basic building blocks of classical computers. The basic building blocks are transistors or MOSFETs nowadays. A transistor or MOSFET is, at the end of the day, nothing more than a switch, right? And the switch can have, let's say, 2 different values or 2 different states. It can be, let's say, open, let's say, this we call, let's say, state 0, for example, and closed, which we call state 1. So these are the 2 possible states or values of a classical transistor. And then, with these switches, we can already do some mathematics. We can do some Boolean logic, which is a basic building block of doing computation, right? For example, let's say this circuit on top of here, this switch circuit on top of here, represents an OR gate, right? And you can actually see if, let's say, switch 1 or switch A and switch B is 0, so the switch is open, 0, the output is 0. If one of the switches is closed, so if, let's say, switch B is closed or switch A is closed, the output is 1, so meaning that the current can actually go through. And if, of course, both of them are closed, it's also 1. And this is actually the truth table of a typical OR gate. An AND gate, we can actually produce in the same way, or in a very similar way. In this case, we just have 2 switches in series. So also here again, switch A is closed, switch A is open, and switch B is open. The output is 0. If one of the switches is closed, so switch B or switch A is closed, the output is still 0. Right? So there's still no current going through because still one of the switches is open. In the case where both switches, switch A and switch B, is closed, we get an output of 1. And this, as mentioned before, are, let's say, the basic gates, including, let's say, a NOT gate, with which we can actually make any type of calculation in a classical computer by just putting this type of gates together. We can actually show that we can do multiplication with this. We can show we can do addition with this, or any type of other calculations. To actually do this type of calculations, we actually scale the computer, right? And just have, let's say, multiple gates in series. So we have some AND gates, and depending on the outcome of the AND gates, there will be OR gates afterwards, NOT gates, and so on and so forth. So there will be, let's say, the gates which we apply are applied in series. to form, let's say, very complex calculations and algorithms which are using in our, let's say, daily life when we're using a computer. Of course, let's say the more complex computation you want to do, the more complex the processor has to be. And for this, or let's say an idea of this, how this is actually scaling over time, the complexity of the processor, which is depend on the numbers of transistors on a single chip, is actually shown in this Moore's law. This here shows the Moore's law, and we see on the x-axis is the time until 2020 in this case, and on the y-axis is the logarithmic scaling of the numbers of transistors within a single chip. And we see that we are already, let's say in 2020, and we see actually that it's actually scaling exponentially, because let's say this is on the logarithmic scale, the y-axis, it's scaling exponentially. And we already are, let's say, at a count of about 50 billion transistors on a single processor, which is an enormous number. And the reason why we can actually, let's say, put more and more transistors on a processor is because we can shrink down the sizes of this small building blocks. So the sizes of the small transistors or MOSFETs, we can shrink them more and more and more. However, there's of course a natural limit for this, right? Which is the size of atoms or the atomic size. And we are very, very close to it right now. So there's not too much room we are actually left to scale processors further. To still actually advance in this computation, we actually have to find a different way to actually do this. Additionally to this, let's say, classical computers are very good for certain type of problems when, let's say, there's brute force calculations. However, if there are, let's say, problems like finding a needle in a haystack, this is a very difficult problem for a classical computer. Because in a classical computer, it has to look at each individual piece of hay to find the needle. And this is extremely resource intensive. What does this actually mean? Let's say how, let's say, the calculation of a classical computer is different from a quantum computer. One can actually somehow see this in this, let's say, very simple example with this 2D maze. So assuming we have, let's say, here a 2D maze with one input and three outputs, right? However, only one of the outputs is connected to the input. And we want to know which of the output is connected to the input. What we have to do is, so from the input, find our way to the output. A classical computer would do it in the following. So it will just take a guess, or let's say go in and then just sort of flip a coin and say, okay, it goes left or right. It goes left in this case. In the next section also flips a coin, which direction it's going, and so on and so forth, and tries actually to go around all possible paths within the maze to find the right solution. Of course, this is also extremely resource intensive because it has to go through each individual path. For this simple 2D maze, maybe it's still doable, but for much, much larger systems, it's not possible anymore. A quantum computer works absolutely different. In a quantum computer, because of, let's say, certain quantum properties, which we talk about in a second, the quantum computer can actually go all paths at the same time, as it's shown here, for example. It goes all possible paths within the maze at the same time. And then, when it's actually finding the exit, the wave function, or the path, because I can actually measure then the exit, the path will collapse to the right, to the right path, which connects the input with the exit with the output. And this is, let's say, sort of illustrates, let's say, this idea or the power of quantum computing, which also is fundamentally different from classical computing. Okay, let's see how we can actually, or where we can actually utilize this quantum computing, because for doing quantum computing, we need actually a quantum system. And we actually know that, let's say in our daily life, there's no, let's say, quantum system at, let's say, room temperature available, right? At 300 Kelvin or, let's say, 20 degrees C, everything behaves classically. To actually bridge this, let's say, from our classical world to the quantum world, so actually go from, let's say, here, right, from the classical world over to the quantum world, where everything is a little bit fuzzy, right? And we have here, for example, also the Schrödinger cat. We have to do something to actually walk from, let's say, one world to the other world. And what we have to do is we have to decrease the temperature. So let's say take out the energy of the system. In particular case for, let's say, superconducting qubits, we go from, let's say, room temperature, which is about 300 Kelvin, down to about below 10 millikelvin. 10 millikelvin is a thousandth of a degree higher than absolute zero. So it's just barely above 0 degree Kelvin, so above absolute zero. One way also to think about how, let's say, the system becomes more quantum mechanical is by just looking at the de Broglie wavelength. So here is the expression for the de Broglie wavelengths. Maybe just a reminder, de Broglie wavelength associates that, let's say, particle can have also wave characteristics. So there's this particle-wave duality usually. And the, let's say, wave characteristics or the wavelengths is actually determined by this de Broglie wavelength. We can rewrite this de Broglie wavelength in terms of temperature. That's then the thermal de Broglie wavelength, which is shown here. It's exactly the same, but we just have rewritten it in terms of temperature. And we see there already that if we decrease T, so if we make T, the temperature, smaller and smaller, the wavelength is starting to increase. So meaning the quantum mechanical properties, which is associated, for example, to the wavelength of the particle, is increasing. So the system becomes more and more quantum mechanical the further I go down in temperature. For example, already at around about a Kelvin or a few Kelvin, for certain materials, I already enter the quantum world. For example, when materials going from a normal conducting state to a superconducting state. For aluminium, for example, which is the typical metal which we are using, this happens at 1 Kelvin. And then down here at the, let's say, very cold plate, the millikelvin plate, we have the quantum processor, which is the heart of a quantum computer. Right? And this is a picture actually which we have of one of the quantum processors which we have developed in our lab, as is shown here. That's a small chip here, and then there are these connections to the outside with RF connectors. And if we zoom in onto this chip, we actually see here a typical qubit. Right? A qubit is similar to a classical bit, with the only difference, it's a quantum mechanical bit. What this actually means, I can try to explain here. So one of the, let's say, earliest qubits were the so-called flux qubits. And the idea of them is actually shown here. So we have a superconducting closed circuit. In this case, let's say a ring, which is actually, in this case, a square. It's not really a ring. And as you actually know, in a superconductor, current can flow inside the superconductor without resistance. Right? So, meaning if, let's say, a current flows in the superconductor, it will continue to flow inside the superconductor, always. And we can actually then also build or think about building a qubit out of this, or a system with two different states. So, for example, one state could be that the current goes around the qubit in the right direction, as it's shown here, right, in the right direction. And let's say, which we, let's say, call state 0, for example. Or the current goes in the left direction, right, as shown here. If the current goes in left direction, we call it 1. This is very classical still. The quantum mechanical part comes in the superposition of right and left. So in this quantum mechanical system, the current can actually go left and right at the same time, as it's shown here. So it goes in the, let's say, right direction and in the left direction at the same time. So meaning the state which we actually have is a superposition out of the state 0 with a certain amplitude, A, plus state 1 with another amplitude, B. And this is the superposition state. And if I can actually make a superposition, I can also make interference. Okay, what does it mean, interference? Maybe just also it's from the, let's say, more classical picture of light. So if I have, let's say, light field and I have, let's say, a double slit in there, a plane wave is hitting the double slit, and then after, let's say, in the far field, after some propagation length, we put in the screen, I would see this interference picture, and this interference fringes here. This is so the well-known Young's double slit experiment taught in Physics 101. What is and this is done with sort of the wave picture of light. However, we also know actually that light is made out of photons, individual photons. So what would actually happening if I'm not anymore in this picture where I can use the wave, the Maxwell equations to describe my light field, because I have a limit of let's say very, very low intensities. We have just single light wave packets, single photons, as shown here. So you have, let's say, emitter, which emits single photons, and then the single photons go through this double slit experiment here, to this double slit, and then hit later on a screen. My question now is, if a single photon goes through the slit, goes through this slit or through this slit, would I actually see an interference pattern here? Right? Because the single photon has to interfere then with itself. Well, let's take a look at the experiment and see what's coming out. So in the experiment, you actually see a screen which shows the distribution of the photons, of the photon clicks, hitting the screen when it's actually going through exactly this double-slit experiment. Photon by photon. It's not so that more than one photon is in the experimental setup here at once. And here is what you're seeing. You see that we are counting these individual photons. These individual photons on the screen are these yellow spots. And you also start to see now that there this interference pattern forms. So this photon, in fact, does not go through a single slit. The single photon goes to both slits at the same time. So also there we have the superposition, in this case in space, that the photon goes in the right slit and in the left slit at the same time. And then interferes with itself at the far field on the screen, as it's actually shown here very nicely in this interference pattern which we are seeing in the far field of the screen. The same is not only true for photons, right? The same is also true, for example, for much larger particles like atoms. For example, here we have a gas of atoms, and we trap this into two slits, this gas of atoms. If you now switch off the trapping potential and have, let's say, the gas of atoms escape these two boxes which are in there, they will start to, let's say, just expand and overlap, as it's shown actually on the right side. Yeah. This is what we observe typically from a let's say, cloud or gas of atoms. So you can think of, let's say, I have let's say, a cloud of atoms, or let's say some smoke, right, in one box and another smoke in the other box. I open the box and the smoke will just start to combine and form a big cloud, right? Same here. In this case, we have, let's say, atoms confined in a laser field, one laser field in the box, another laser field forming another box. Switching off the boxes, they will start combining and form, let's say, this cloud here. That's not very exciting. However, if you now decrease the temperature of the atoms so that the de Broglie wavelength becomes dominant and the particles become more quantum mechanical, what we actually see is this interference. You can see here very nicely interference pattern of atomic matter waves. This actually is a picture we have done in our lab, and always or it shows directly the, let's say, constructive and destructive interference of atomic matter. Right. So it's a real, let's say, matter wave interference of real matter. In this case, about 10 to 6 atoms in the bosons and condensate. Yeah, here, for example, shown again how this interference is working. If you have a wave function here, similar to, let's say, this cloud of atoms, a beam splitter is actually going through the beam splitter, and we see this interference pattern forming. Then, if we will actually do a measurement, so this is actually the wave function, right? The wave function has this interference. If you're doing a measurement, then this wave function will collapse to a single point, as shown here, for example. That's then, let's say, where we are measuring it. And this is similar to, let's say, the superposition principle, which I've just described right now. And various physical systems, also on, let's say, a qubit, as in the earlier examples. Exactly, this is also used in this, let's say, calculation of the exit of the maze, what a quantum computer is actually doing. And then the wave function will, when I measure the wave function, the exit of the wave function will collapse to the right path. Okay. Another way to actually see the power of these quantum computers is to look actually at the possible number of states that a system can actually have. For example, let's say, single qubit, similar to a bit, can only have two different states. However, let's say a system with two qubits can already have 2 to the power of 2 different states, so 4 different states. So a system with n qubits will have 2 to the power of n different possible states. Right? For example, just to remind you, I can actually, with this different states, could represent a way in the maze. Right? Why this is actually significant? Here the example. If I have, let's say, there's a medium scale quantum processor with 300 qubits, the system can actually represent 2 to the power of 2 times 10 to the power of 90 possible states. This is an extremely large number. As a comparison, in our universe, in the observable universe right now, we only have 10 to the power of 82 atoms. Order of magnitude smaller than the states which are possible to be represented in the 300 qubit system. So this also shows the, let's say, vast superiority of a quantum computer compared to a classic computer. This number of states can never be represented in a classical system. But just looking at, let's say, the number of atoms which we have, right, in the universe. And this also shows that, let's say, with the, let's say, classical computer, we can only solve, let's say, certain type of problems. It's called p-hard problems. Whereas with a quantum computer, we can solve a much larger class of problems. One of this, let's say, let's say, an application of this, let's say, problems which you can solve with a quantum computer is, for example, simulating chemical processes. For example, the fertilizer. Producing fertilizers is actually done by nitrogen fixation, right? And this is, let's say, very important, this production of fertilizers, because we actually need it to produce, let's say, food for everybody. However, this production is energetically very inefficient as of now. And if we are doing it on industrial scale, or it's actually done in industrial scale, and uses about 3% of the world's energy consumption just to produce those fertilizers. 3%. It's an extremely large amount of energy which is being used for this production. So it would be much better if you find a way to do this more efficient. And in fact, we actually know that there is a way. We actually know that bacteria is doing exactly the same process, producing these fertilizers on their own in a much higher or much more energy efficient way. And they're using sort of a molecule for this, which is called nitrogenases. However, it is not possible to understand the, let's say, chemical process, which actually does exactly this in this bacteria. Because a classic computer is not able to actually simulate this chemistry, which is quantum mechanical. However, on a, let's say, moderate quantum computer, this becomes possible. So this actually shows that, let's say, with a reasonably moderate quantum computer, in the terms of size of 400 qubits, we are able to already solve problems, or let's say humanity greatest problems. We can actually also look at other problems like carbon capturing, which is associated to global warming, search for high temperature superconductors, and so on and so forth. In fact, there's a vast area of applications for quantum computing, for medicine, AI, banking, financial systems, communication, cryptography, logistics, and of course, military and defense. Okay, so how close are we in terms of quantum supremacy? This is actually a fairly old example, but we are roughly still there, maybe a little bit closer. So in 2019, there was, already 6 years ago, this quantum processor from Google with 53 qubits. And it was tested against, let's say, the most powerful supercomputer in the US, the Summit in Oak Ridge. And there was, let's say, some abstract mathematical task given to these two computers, to the quantum processor with just 53 qubits, and to this supercomputer in Oak Ridge. And the quantum computer could actually solve the task in 200 seconds. Whereas the system in the Oak Ridge system, the supercomputer, would have needed 10,000 years. So it could not even complete this task at a small fraction. Right? It was totally overwhelmed with this task. However, this was, let's say, a few years back when there were only 53 qubits available. Nowadays, the systems have actually 50 to about 120 qubits. So they're much more powerful than SM. And this actually shows where we are right now. This is, let's say, an idea of the comparison of the, let's say, supercomputer and a quantum computer, and how much, let's say, for a certain amount, or let's say certain task, a classic computer actually needs to simulate. So, for example, a 60-qubit system with n numbers of cycles will need 1 minute, and so on and so forth, to hear about 10,000 years, which was the example we just had discussed before. So it's a 50-qubit system with about 20 cycles. Memory requirement a couple terabytes for the classic computer. If we just increase a little bit the number of qubits, going to 70, for example, we are already deep in the supremacy region. So deep in the supremacy region is where a classic computer would actually need more than 100,000 of years to complete this task. So well beyond the limit of any meaningful calculation. So meaning actually the systems we can actually build nowadays could actually solve problems much more efficient than a classic computer for certain type of niche applications. And this is actually sort of a diagram of the roadmap of quantum processors in the next few years. So this roadmap until 2029. As mentioned before, we are right now here with about, let's say, 100 qubits, 10 to the 2 qubits. And in the next few years, we will actually witness that we pass the 1,000 qubit mark and then go to the 10,000 qubit, 100,000, and to the 1 million qubit mark, where we have a fully error-corrected quantum computer. This is, as mentioned before, the hardware roadmap by Google. Similarly, there are, let's say, roadmaps by IBM, there are roadmaps by IQM, and so on and so forth, which are very, very similar. Right. However, of course, to actually go this long way to, let's say, thousands of qubits, there are still open questions which we have to resolve. These open questions is something which we are also doing, let's say, in our research team here in Singapore. Maybe just, let's say, go one step back and let me emphasize a little bit that typically what prevents us from, let's say, exceeding in a, or let's say from getting a new technology is usually the hardware. This is true, let's say, for a fusion reaction or for anything else. One example is, for example, or shown here, there is a theory which predicts that it's actually possible to break the speed of light limit, or the so-called Robb barrier limit, by not by, let's say, moving faster than the speed of light, but let's say not moving within the space, so within, let's say, a small sort of Robb bubble. This was discussed by Eric Lenz in a publication a couple of years ago. Let's say on paper, this is possible. It's feasible to, let's say, have something which moves, let's say, out of, let's say, our normal space faster than the speed of light. However, it would actually take quite some energy, right? In this case, actually, for example, to drive something, let's say, yeah, faster than the speed of light, with a, let's say, 100-meter radius, we would actually need roughly the rest mass energy of 100 times of the mass of the planet of Jupiter, or let's say a fraction of the sun. Which of course is possible in theory, but there are some practical limitations to this, obviously. So meaning actually the hardware to develop this is very unfeasible. Another example is the detection of gravitational waves, right? In fact, actually, with this, let's say, to detect a gravitational wave, one has to measure the length change of a 4-kilometer long interferometer arm, 4-kilometer long interferometer arm, and the length change has to be a fraction of the proton radius. Proton radius is about 15 femtotesla, 15 times, or let's say 5 femtotesla, sorry, 5 times 10 minus 15 meters. Which is extremely small, especially on this very large 4-kilometer interferometer length. However, this was actually accomplished. And we actually have seen a couple of years ago the first measurement of gravitational waves. Although, let's say, initially it looks very difficult to realize with, let's say, persistent work and everyone working in the same direction, it actually is such a large effort on the hardware development becomes realistic, right? And this, let's say, also, let's say, the research efforts which are going now into developing, this larger quantum computers. Although from the perspective right now, it looks like there's still a lot of things to do to go to this 1 million qubit scale quantum computer, but it's not totally unrealistic. In fact, actually, there's no let's say, physical law limiting us to say that we cannot reach it. Okay, so for the superconducting systems, let's go back to this. We let's say, producing them, and the idea there is, let's say, similar to what I said before. We have a superconducting circuit, which is an AC resonator, which produces actually a harmonic trapping potential, or let's say harmonic potential with equidistance energies. However, since they are the equidistancy energies, they are not very useful as qubits. So we have to, let's say, break this symmetry in the energy spacing or energy difference by implementing, instead of a linear conductor, a linear inductor, a nonlinear inductor, which is a Joven junction. And with this, we actually be able to have, let's say, the anomalicity in the energy states of the superconducting circuit, which in this case is a superconducting qubit. And based on this technology, we actually have two main setups in Singapore. One is our, let's say, circuit lab, where we perform experiments or trying to develop hardware to scale the quantum computing system. And the other part is the processor operation platform, where we have a fully functional quantum computer, which researchers in Singapore can actually use to test, let's say, algorithms, to test error correction codes, to test mitigation strategies. This is, let's say, a typical picture how let's say, how a quantum computer is structured. And we see we have, let's say, a part which is the core, the processor unit itself. One part which is the classic control of the processor, to actually write there the superposition state, read out the superposition state, produce the entanglement between the qubits. And then the, let's say, highest level part, which is the user, which just wants to run, let's say, an algorithm on the full system. In the lab, we actually produce our own quantum processors. So we have a fabrication facilities within the lab. So we do, let's say, the design and architectures of the processors, the fabrication and packaging of the processors, and then, of course, also the measurement and the characterization. Additionally, we have developed, let's say, further, let's say, more advanced technologies like air bridges or flip chip technologies to make these processors more and more compact and be able to scale further. Additionally, we also have developed the electronic control system, which is based on an FPGA system with 16 digital analog converters and 16 analog digital converters, which can actually generate this signals needed to manipulate the individual qubits. This is actually how it actually looks like. And we see here this FPGA systems, FPGA 1, FPGA 2, which generates this microwave pulses, which we will send inside here to the sample where the quantum processor actually sits in the 10 millikelvin environment. And this system is very scalable and flexible, scalable up to, let's say, a few hundreds of qubits. And we can already, let's say, with this system in place, do some, let's say, very fun algorithms. For example, here the Gauss sums factorization, which, let's say, works as following. So we have a qubit, and there we implement a certain byte sequence. And then after implementing this byte sequence, we can actually encode into, let's say, this qubits a certain number. For example, here, we wanted to test, let's say, this number here, which is shown here, and look actually at the factors of these numbers, or calculate the prime factors of these numbers, which we can actually calculate by implementing this equation here in a byte sequence. And in the measurement, we actually see if the, let's say, signal from a particular number is above a certain threshold, it will be a factor of this large number. And with this, it's sort of a very simple implementation of using a quantum system, quantum computer, for factorization of a large numbers using Gauss sums. And this is sort of where we are right now. In the future, to go actually to this much larger scale systems, we develop also readout electronics in the cryogenic environment, cryo-CMOS systems, and also systems in the millikelvin environment, which are based on superconducting logic, the so-called RSFQ logic. If you go even one step further, so if you have, as shown before, let's say one quantum computing system here, and let's say another quantum computing system here, we want actually that these two systems start to communicate to each other, with each other. And this is extremely difficult because this communication now should not be classical. So it should not be that the classical information is being shared between these two quantum computers. It should be quantum mechanical communication, or there has to be a quantum mechanical link between these two quantum computers. Making this quantum mechanical link is non-trivial at all. One way to, let's say, think about doing this is to do it with either cold atoms or with atoms, because we actually know these atoms can be very quantum mechanical, and we can, let's say, generate or let's say use this as an interlink between two different superconducting quantum computers. Maybe let's skip over this. And actually, we have shown that it's actually in principle possible to use this, let's say, either cold atoms to interlink to quantum computers. However, the experimental realization is still something which we are working on. This was, let's say, the first system we have in Singapore. The second system is this processor platform, which we have discussed before. In this processor platform, which is open to, let's say, researchers within Singapore to actually use, we have 3 processors. One is a small scale system, a 5-qubit IQM Spark. Then we have an 8-qubit system developed by ourselves, and a 20-qubit system also from IQM, where one can run a little bit larger codes. This whole setup can be actually, in future, will be actually extended to much larger quantum processors. So this is just the start. And the system is online, can be accessed from over the cloud with, let's say, all parameters visible, like, for example, the temperatures, the QPUs, the T1, T2 times, and so on and so forth. And then actually we also run automatically, let's say, all these calibration codes, which are integrated into the software package which we actually have. For example, here is, let's say, a decimation between two qubit states. Let's say state 1 and state 0. So that depending actually on the measurement, we can actually say that the system is in one of these two states. Okay, so so this is, let's say, one example where we actually did some measurements on the qubits, and we see this very nice behavior with the flux. We can shift the frequencies of this 5 and 20 qubit chip. Okay, so in the last 5 minutes, right? So I have 5 minutes remaining. Let's see what else we can actually do with this nice superconducting quantum system. And this is, let's say, a little bit more on the fun side, right? Not too much on the, let's say, hard research side. So what else can we do? Okay, so we have this qubits, which is shown here on the left side, which are working at this 10 millikelvin temperature, so extremely low temperatures, just barely above absolute zero. And the idea is maybe to bring some biological systems and try to entangle this with a qubit, right? As a biological system, one idea is actually to use tardigrades. Tardigrades are 8-legged invertebrates, and they have a size of about, let's say, 100 micrometers. So the size is similar to the thickness of a hair. And these are actually one of the most resilient multicellular organisms which we have on planet Earth. And the experiment we have done is the following. So we had this qubit here, a transmon qubit. We put the tardigrade in between these two electrodes. I think it's shown here in the picture. So this is the tardigrade. These are the two electrodes. Here's the Josephson junctions. And these electrodes, when the qubit is in a superposition state, also the electric field of the electrodes is in a superposition state. And with this, the tardigrade will see this superposition of the electric fields and will actually also influence the superposition just by the fact that the tardigrade is inside this field. So the dielectric properties is actually changed by the presence of the tardigrade. And what we actually see is that with and without the tardigrade, the qubit frequency is actually changing, as it's shown here. And we can actually also write this in a microscopic model. For example, the superconducting qubit you can write as the following: just a normal two-level system, and the tardigrade as a collection of harmonic oscillators. This is, let's say, the total Hamiltonian of the coupled tardigrade qubit system with this coupling here. And then we can do second-order perturbation to solve this Hamiltonian, assuming we have weak coupling. And what we're getting are dressed states, which are very isolated environments. So the system is actually a dressed system. One could say that the qubit is dressed with the tardigrade, producing new energy eigenlevels. What we did then is, so we had, let's say, the dressed system here, the dressed system of the superconducting qubit with the tardigrade, and let's say a normal superconducting qubit. And we could actually entangle these two systems with each other. So we could entangle the normal superconducting qubit with the dressed system and produce actually a Bell state. A Bell state of including these two entities of tardigrade superconducting qubit system and superconducting qubit, with a, let's say, fidelity of about 82%. So this actually shows that this, let's say, quantum properties can actually be, let's say, are very dominant at the low temperatures, but also some organic systems can be entangled as well. And let's say the absolutely interesting part is, as it's shown here, after, let's say, these measurements of about 420 hours, and the tardigrade was at 10 millikelvin this whole time, we have actually warmed it up, the tardigrade, and it came back to life. And this is actually this tardigrade here. So this is a picture of the tardigrade, or the movie of the tardigrade, and you can see actually it's moving and looking for food. So actually, after, let's say, cooling down to this millikelvin temperatures, doing this entanglement with the tardigrade, we actually warmed up the system, and the tardigrade was coming back to life after about 1 hour. In fact, this is actually was the first demonstration of an organic system to be at this extremely low temperatures and then coming back to life. Okay, so now let's step a little bit back and say, okay, so what we want to do in terms of research in future is enhance the capabilities, of course, of our superconducting circuits, and also explore a bit further the path towards connecting, let's say, atomic systems and superconducting quantum systems. That's all I would like to share. And thank you for your time. Okay. And happy to answer any questions.
Okay. Thank you, Prof. Reiner, for your interesting and enlightening presentation today. And today's talks give us valuable insights about the introduction of the quantum computing, particularly about the superconducting quantum processor, and also the current state-of-the-art quantum computer in Singapore, and also the future directions. And to all the participants, we now have 30 minutes for our questions and answer sessions. So if you have questions, you can either post your question in the Zoom chat or raise your hand if you would like to ask your question directly to the speaker. I see we have a question in the Zoom chat. Let me read out. First is the question come from Muhammad Taufiki. The question is, how much can we actually control the preparation of qubit amplitude parameter with today's quantum computer?
Yeah, this is a very good question. So maybe let me reformulate this. At the end of the day, the question asked, what is the fidelity of our quantum states which we can prepare? So how good is this quantum state which we can actually prepare? And the fidelities for, let's say, the single qubit preparation are in the range of, let's say, 3 nines. So let's say 3 to almost 4 nines. So 99.9%. So if you, let's say, want to, let's say, prepare the state 1, it is in the state 1 at 99.9%. And which is, let's say, important because if we, of course, do a lot of operations, this will actually scale with the number of operations which we are producing. So the control is not absolutely precise, but it's actually good enough to be able to do algorithms on a quantum computer. Especially, let's say, in future, when we can implement error correction codes, then actually we can be a little bit more relaxed on this, let's say, initial control of the state preparation. I hope this answered the questions.
Okay, thank you. Okay, thank you, Prof. Rainer, for the explanation. Is there any comment from Muhammad Taufiki? The answer is okay. Thank you for the answer, Prof. Rainer. And maybe I would like to follow up a little bit. How about you mentioned about the qubit fidelity or the gate fidelity. Um, how do you measure in the percentage or something like this only you define with qubit fidelity, for example, 1 or 0 and so on?
Yes, so let's say how we're measuring this gate fidelities, it's non-trivial. There's this so-called randomized benchmarking, which one is using. So for example, let's say we start with a qubit in a particular state, let's say in state 0, and we apply a sequence of gates to it. Let's say a sequence of, let's say, 100 gates. And this sequence is done in a way that we apply the gates and then also the reverse gates. So at the end of the day, the qubit should be exactly in the same state as it started. And what we can actually measure then, after this, let's say, large number of gates, is then if the qubit is in the state or not. If the qubit is not in the state, then we can say, or let's say, doing a statistics on this, we can actually give a certain percentage of, let's say, how bad this gates were, let's say, this bait sequence actually was. And this gives us, let's say, an idea of the quality of the gates and the fidelity of the gates.
Okay, thank you for the explanation, Prof. Rainer. And there is a question from the Zoom chat from Prof. Bambang Ariwahjudi. So the first question is, what superconducting material type is preferred, ceramic or metallic? And then the second one is, what are the main sources of error which need to be corrected so far? Thank you.
Okay, yeah. So maybe let's go to the first question, which is a hardware question. So in terms of materials, right now, typically metals are used. So high temperature superconductors are not used right now because they have also some defects, whereas metallic type 1 superconductors are much better. They also don't have vortices, or let's say much lower number of vortices. One of the big problems in this type of materials are the so-called two-level fluctuators. They actually form when I have let's say, a metal, let's say, aluminum film, which generates the qubit. And this aluminum film oxidizes naturally. And typically, since this oxidization is very amorphous, there are some defects in this oxide layer. And in these defects, because there may be some loose bonds, they can actually behave like two-level systems. Similar to this quantum, let's say this qubit two-level system. It's also a two-level system. And they can start to interact with each other. And this can be part of, or let's say, yeah, can be part of this so-called decoherence. So if I, let's say, prepare a certain state in my qubit, and this interacts with, let's say, another two-level system here, which I don't have control of, then let's say this total state of my qubit is being scrambled. That's sort of right now one of the challenges we have. Metals which we are using are aluminum, typically. So that's the most common one. But now there's more and more the direction going to tantalum instead of aluminum. Yeah, I hope this answered the question. The second question was, what is the main source of errors which need to be corrected? Yeah, so there are, let's say, various type of errors. Typically, when we sort of discuss about qubits, we say we have a T1 time and a T2 time. T1 time tells us if I, let's say, prepare a state of the qubit, let's say state 1, how long does the qubit stay in state 1? And as of now, it's the let's say of a large chip, maybe let's say with 50 qubits, typically T1 times on the range of let's say 50 to 100 microseconds. There have been experiments for single qubits where T1 times up to milliseconds were seen. So it's already fairly long. So this tells us roughly what can be the T1 times in the future. This is the bit flip. The other very important time scale is a so-called T2 time. T2 time tells us if I, let's say, prepare the qubit in a superposition state, how long will it stay coherent in the superposition state? So phase coherent in the superposition state. And if I, let's say, if there are some, let's say, environmental fluctuations, this will actually destroy the superposition state or smear out the superposition state. And this is given by this T2 time. And there are also, let's say, noise from the external environment can actually play a role. These two-level fluctuators can play a role, or other yes, physical environmental effects, magnetic fields, for example, as well. So these are, let's say, the most sources of errors right on the superconducting systems. Having said this, there's also technical errors, like, for example, crosstalks. So if I prepare one qubit, because everything is an RF, it's a microwave, right? Microwave goes everywhere. So if I prepare one qubit, it's possible, let's say, that the neighboring qubit will be influenced by this as well. So it's yeah, engineering problem to really minimize this crosstalks as well. Yes. Okay, I hope I've answered the question.
Thank you, Prof.
Thank you.
Thank you. And can I follow up a little bit about the source of the error, Prof. Rainer? If the error is come from, for example, qubit, or in the gate operation, which is, if I look at the circuit lab, there is a three-part software, classical controller, and also quantum processor. So if the error is come from the qubit, so it will exist in the quantum processor. So how to integrate the error mitigation or error correction code in the system?
Very good. So to actually integrate, let's say, an error correction code, one needs a minimum fidelity for the gate operations, right? Okay, assuming we have this minimum gate fidelity, then what's actually possible is to, let's say, the most simple one, is to try to, let's say, spread the, let's say, a single qubit to, let's say, a collection of qubits. So for, let's say, a single qubit system, we can actually spread to a collection of, let's say, 5 qubits. And in this 5 qubit system, what we can actually do is we can encode the state into, let's say, a 3 qubit state, for example, and look actually at the parity of this yeah, at this state. So we could say, okay, only let's say the state 0 and 1 are, let's say, in the 3 qubit state, let's say, states with even parity, right? 1 1 1 and 0 0 0, for example. If there's a bit flip, it will be actually an odd parity state. And by just let's say, having, let's say, a clever way to measure the parity, we always actually know if there's an error has occurred or not. We actually know if there was a bit flip inside the state or not. And this is sort of one way to, let's say, a very simplistic way to implement this type of error correction. To actually try to spread out this qubit state to multiple qubits and do some, let's say, measurements on the qubit, which does not give you the knowledge of the state itself, but only gives you the knowledge if an error has occurred or not. That's sort of the basic idea.
Okay. Thank you, Prof. Rainer. And there is another question from Dr. Hamzah Fauzi. Thank you for your insight. And I have two questions. The first question is, what makes the tardigrade a quantum object at low temperature and be entanglement with the qubit. So this animal, why
Right.
can be used to entangle the qubit?
Right, right. Yes, so yeah, so I mean, this was a fun experiment, right? So there's not some deep philosophical things behind it. However, if you actually have, let's say, this tardigrade, and we cool it down to, let's say, this mitigating temperature, then actually the system is in its ground state. So everything, let's say, all the molecules are in their low vibrational ground state, which at the end of the day, and let's say, since it's in low vibrational ground states, the next higher energy states are actually harmonic. So it's a very good harmonic oscillator. And it's that's a very good the quantum mechanical harmonic oscillator. And this is actually how we, let's say, have described the systems as a collection of quantum mechanical harmonic oscillators. And this makes sort of, yeah, let's say just the yeah, temperature itself, that is at this very low temperatures, it makes the system quantum mechanical because we take out the temperature.
So isn't it can increase the qubit lifetime if we entangle with this animal?
Well, we didn't see a large decrease in the qubit lifetime. Let's put it this way. Of course, let's say we let the qubit interact with this larger bath of harmonic oscillators. So we would actually expect there some leakage of the state towards the harmonic oscillators. But this was still reasonable. So we didn't see a sort of large interaction with the environment. So if it's just a few of these harmonic oscillators interacting with it, it's something which you can actually, yeah, does not affect the qubit too much. Unfortunately, it's not extending the lifetime.
Okay, so it will reduce the coherence time.
It will reduce a little bit of coherence, yes.
Okay. Is there any follow-up from Dr. Hamzah
Oh, thanks.
about the first
This
question?
is just the assumption, right? So we assume that the animals goes to the ground states. There is no way that we can measure or verify that the animals goes to the ground states.
Well, it's at mid-Kelvin temperature. So this is sort of, there's no excitation in the system.
All right.
Yes. So this is something which we know, yes.
I see. But
Okay.
this capacitively affect the superconducting, right? Qubits, so it shift the resonance. I mean, can we explain just simply, I mean, classical capacitive coupling or no?
Yes. I mean, so okay. So we have a capacitor. Inside the capacitor, there's a dielectric medium. And this dielectric medium will change the capacitance. That's
Right.
correct.
Yes.
But we can also, let's say, that's sort of the typical classical explanation. But we can also try to, let's say, get a quantum mechanical explanation of the or let's say microscopic explanation of the dielectric medium. Which, if you, let's say, go through the math, it is, let's say, we can actually describe it by a collection of harmonic oscillators, which is sort of similar to this. Yes.
Okay, thank you.
Okay.
Okay, thank you, Prof. Rainer. And the second question from Dr. Hamzah is, will the qubit be open to researchers outside Singapore in the near future?
Yes, in principle, sure. We have some, or we're starting with some collaborations also outside of Singapore, and happy to, let's say, work together and have, let's say, the processors open to, yeah, and anybody who's actually interested in it.
Okay, thank you. And there is a question from Dr. Ago again about this tardigrade tardigrade again, this animal again. So I did not quite follow the part of tardigrade. And did you create entanglement between the superconducting qubit? Yes, I think yes. And a living tardigrade. So if so, how do you verify? This is the important question. How do you verify the entanglement exists?
Yeah, it's a very good question. So the things which can actually verify are the following. So we could actually verify that the, let's say, qubit was, let's say, interacting with the target rate. This we have seen because the frequency of the qubit has shifted when you put in the target rate. One way to describe it is actually describe it in this microscopic model to say, let's say the target rate is this harmonic oscillator and the qubit is this two-level system. So, and with this, we can actually have, let's say, overall a dress state system. Then what we actually could verify, or we did as well, is that we have another qubit and have this other qubit entangle with this dress state system. And this we could actually verify. So we did actually, we generated base state and did a, let's say, Bell measurement. So we actually measured the state of this, let's say, two coupled systems and verified it's actually in a Bell state. So this is what we have done. However, we are not able to measure the, let's say, target rate on its own. So we could only measure it with the help, let's say, of the other qubit, for example, not the target rate itself. That's sort of, I agree, that's sort of a weak point in the experiment.
Okay, thank you, Prof. Haidar. And the next question again from Muhammad Iman Sah. Mas Iman, do you want to speak directly to Prof. Rainer? He
Yes,
my previous RA that applied to your lab previously.
yeah, thank you very
Okay.
much, Dr. Gagus, for the opportunity, and thank you for the insightful presentation, Prof. Renner. And I'm interested in the analysis of the tardigrade for the microscopic model. And could you please explain more detail behind modeling the tardigrade as a collection of harmonic oscillators or electric dipoles in the quantum framework? And can we see any difference in the maybe the quantum circuit if we use qubit and tardigrade, or we can just see the difference in the equation or maybe another representation? Thank you.
Okay. So yeah, so maybe let me maybe share the screen for a second. I have this one here. Okay. Oh, this is Ranga, by the way. Okay. So yeah, so this is actually the model which we have. So the normal two-level system and the collection of harmonic oscillators with random distribution, a random frequency distribution, omega i's. And this is the, let's say, total Hamiltonian. So when we actually, let's say, calculate the, let's say, energy of the states, we actually see that we get this sort of dressing or splitting of the energy states. And this is, let's say, typically what you have in this, let's say, dress state environment. Where you then, which, if you, let's say, sum it up with, let's say, all dress states, leads to a overall energy shift of, let's say, the first, let's say, ground to excited state. And this is something which, let's say, we could measure. Having said this, let's say we can, let's say, explain this with this, what is it, derive it with this quantum mechanical model. But in principle, one could also just say, one takes just a classical model and says, okay, that's let's say, direct click element inside the capacitor. But since this is, let's say, it has, but this is, let's say, the classical explanation. The fundament of this classical explanation is actually this microscopic model. That's sort of the idea. Yes, and then let's say what we did is generating this Bale state here, and we did a tomography on the states. And we got, let's say fidelity of about 82% for the this Bale state. Additionally, what we did is we looked actually at certain types of entanglements, let's say of the let's say negativity of there's a qubit A with qubit B and tardigrade together, qubit tardigrade and qubit AB together, and so on and so forth. So let's say different pairs, and also at the tripartite entanglement. And let's say depending actually on the let's say at the end of the day number of harmonic oscillators which we actually used, there's always a, let's say, non-zero entanglement. But let's say the higher the number of oscillators are there in the tardigrade, the smaller is actually the entanglement. Sort of that's yeah, the things which we have. Yeah, this is the mathematical model and the things which we have measured.
Okay, thank you, Prof. Einer. We have 4 minutes left. So we still have one question again. I think this is the last questions. So from Dr. Ahmad Ridwan Dresna Nugraha from our Research Center for Quantum Physics, DRIN. Sorry if my question might be far from the topic you have explained, but hopefully it's still related. Recently, we already live in kind of the classical EI era, which supported by GPU or TPU, whose hardware structure is suitable for matrix calculations. However, it is also well known that such calculation with the GPU or TPU devices are energy intensive. So the question is, in the future quantum era, will there be a specific hardware accelerator with architecture similar to GPU or TPU for a kind of quantum machine learning? Or else, would this be some kind of superconducting GPU or TPU equivalent hardware, or are these physical constraints to such device? Thank you.
Okay, not sure if I can really fully answer this question. Let's say quantum computers cannot solve everything, of course. There are only, let's say, certain types of algorithms where quantum computers are, let's say, yeah, supreme to classical computers. One of them, let's say, one of the famous one is this, let's say, factorization of large numbers. Another one, or let's say another directions are optimizations problems, where also quantum computers are much more powerful than classical computers. Simulation of chemical processes. This is also one of the main areas. In, let's say, AI particularly, I think there are some ideas that quantum computers could actually help in, let's say, in the learning of AI models. And then one of the reasons is because, let's say, typically in this, let's say, learning of these AI models, you need, let's say, large correlated systems as your input. And a quantum computer can actually provide, let's say, is one of the bedrocks of quantum computing is that actually can provide large correlated systems, large correlated inputs. And that's actually still part of the research, but it's sort of one direction where, let's say, quantum computing can help within the AI. I'm not sure if it will actually be able to help with matrix multiplication. This I'm not sure. I would actually guess not really. I'm not sure if this answered the questions.
Okay, thank you, Prof. Rainer. Maybe the last question is, because I think also very important. Why don't you think to extract the active crystalline substance from the tardigrade such that we don't need to feed the animal, as well as there is no biochemical complication? So why we don't extract some active crystalline substance from this animal?
So, right. When we have cooled down the animal, I mean, that's sort of very important. So, I'm not sure if this answers the question, what I'm saying now, but let's see. So this tardigrade, when we actually put it into, let's say, a cryogenic environment, it will go in the so-called Thun state. Thun state is a state of the tardigrade where it expels all water from it, and it sort of curls down. So it's a dry piece of matter. Let's say, biologists were not really sure if there are maybe still some processes going on in the tardigrade, right? If it's still a little bit sort of latent alive. But actually in the experiment we have shown, because at this 12 millikelvin, there's nothing moving. So at 12 millikelvin, it's at the ground state, there's no energy in the system. So it's let's say dead as a rock, right? So there's nothing going on. And what we have actually done afterwards is we, let's say, warmed up very slowly the fridge, put actually again air pressure into the system, and then took out the tardigrade and put it into a water in sort of this typical natural habitat environment. And then it went slowly from this Thun state to being alive again, and was then moving around and starting to eat. So this was, I found this very amazing, that, let's say, this creature actually survived this whole ordeal, and was actually really in a state where it was not alive and then alive again. So I'm not sure if this really answers the questions, but yeah.
Okay, is there any comment from Dr. Bambang? If no,
it's okay. Yeah,
okay.
yes.
Thank you so much.
I can understand. Yes.
Okay,
Yeah,
thank you so much. I think the time is up, and thank you very much for your amazing presentations, Prof. Rainer. So I know that Prof. Rainer is very, very busy, and Prof. Rainer still have time for us. So we are very fortunate to have Prof. Rainer today. And thank you once again for sharing your time with us today as our speaker today. And thank you to all the participants for joining us today. And we greatly appreciate your participation. So we look forward to seeing you again at our next Brain Quantum Physics Colloquium. And have a great day, everyone. Thank you.
Yeah, and thank you for inviting me.
Yes.
It was a pleasure to talk to all of you.
Yes.
And maybe at some
Thank
point
you
we
very
can
much.
even see each in
Okay.
person.
Okay. Thank you so much, Prof. Rainer.
See you.
Okay,
Bye.
see you.
See you. Bye.
Bye.